So in this video I'm going to discuss the questions in thermal and statistical physics which appeared in GATE 2022 examination. Okay, so let's continue with the first problem. The statement is, which of the following relationship between internal energy U and Helmholtz free energy F is true? Okay, so let's see how we can solve this problem. The expression for the Helmholtz free energy F, that is equal to U minus Ts. Okay, so that a small change in the Helmholtz free energy dF, that is equal to du minus Tds minus s dt. So from the first law of thermodynamics I can write du, that is equal to Tds minus pdv, that's the replacement for du, and then minus Tds minus s dt. So Tds and Tds, they will cancel, so ultimately we are left with minus pdv minus s dt. Okay, so let's call this as equation 2. So from equation 2 I can write s, that is equal to minus df by dt at constant volume, because when we are keeping the volume constants, this term will disappear, so ultimately s is equal to minus df by dt. Okay, so let's call this as equation 3. Okay, now clubbing equation 1 and 3, so that is 1 and 3 implies f is equal to u minus ts, the u, so replacing s with minus df by dt, so u plus t df by dt at constant volume. Okay, so from here I can write u as f minus t df by dt at constant volume. Okay, so let's call this as equation 4. Now I'm going to evaluate the differential of, that is curly t of f by t, okay, and at constant volume. Okay, so that is equal to 1 by t df by dt at constant volume minus f upon t square, or this is equal to, we are taking 1 minus 1 by t square outside, so that inside we are left with f minus t df by dt at constant volume. Okay, so from here I can write f minus t df by dt at constant volume, so this is equal to minus t square curly t of f by t at constant volume. Okay, so let's call this as equation 5. Okay, now if we just compare equation 4 and 5, so 4 and 5 implies u is equal to f minus t df by dt at constant volume. Okay, so that means which is further equal to minus t square curly t of f by t. So therefore 4 and 5 implies that u, that's the internal energy, that is equal to minus t square curly t of f by t at constant volume. Okay, so therefore option B is the correct option. No, it's no, not option B, it's minus t square curly yes, it's option A, it's with a negative sign. Okay, so option A is the correct option here. So let's continue with the next problem. The statement is, water at 300 Kelvin can be brought to 320 Kelvin using one of the following processes. Okay, so process 1 is water is brought in equilibrium with the reservoir at 320 Kelvin directly. So that means a single step process. Okay, in the second stage, water is brought in equilibrium with reservoir at 300 Kelvin first, and then with the reservoir at 320 Kelvin. So that means the the temperature is changed in two steps basically. Okay, and in the process 3, water is first brought in equilibrium with the reservoir at 350 Kelvin. Okay, so that means first the temperature of the water is raised from 300 Kelvin to 350 Kelvin, and then the temperature is brought down from 350 Kelvin to 320 Kelvin in two steps. Okay, the corresponding change in entropy of the universe for these processes are delta S1, delta S2 and delta S3 respectively. So then which of the following inequality is valid? So for the in order to obtain the correct answer, we have to perform the calculation basically. So okay, so let's continue our discussion with the step 1 or process 1. Okay, so in process 1, okay, so basically we are changing the temperature of water from 300 Kelvin to 320 Kelvin in by following different routes. Okay, so in the first case the temperature is changed from 300 Kelvin to 320 Kelvin in one single step. Okay, the corresponding change in entropy of the water, delta S water, that is equal to dq by T, and temperature changing from Ti to Tf. Okay, now dq, that is equal to the principal heat capacity of water Cw dt by T from initial temperature I to final temperature F. Okay, and that is equal to Cw ln Tf upon T initial. Okay, so now the values of the initial and final temperature, they are given to us. So that means Cw ln final temperature is 320 Kelvin divided by initial temperature, which is 300 Kelvin. Okay, so if we do the calculation, so this number will come out to be equal to delta S W, that is equal to 0.06454 multiplied by Cw. So that's the entropy change of water during this step. Okay, now let's try to evaluate the entropy change of the reservoir, because it's a one single reservoir. Okay, so delta S reservoir, delta S reservoir, that is equal to, because during this process reservoir is losing heat to the water, so that's why we'll place a negative sign in front of dq. So because it's losing heat to the water. Okay, so divided by temperature of the reservoir at which it is losing that heat, and how much heat it has lost, so that is equal to the heat gained by the water, that is Cw delta T divided by temperature of the reservoir. Okay, and Cw delta T, that's nothing but minus Cw, and delta T is 320 minus 300. Okay, divided by T reservoir, which is temperature of the reservoir, this is 320. Okay, 320 Kelvin. Okay, so this is equal to a difference of 10 units of temperature. So that after solving this, delta S reservoir will be minus 0.0625 Cw. So that delta S1, that is the entropy change for the universe, delta S1, that is equal to delta S water plus delta S reservoir. And if we substitute the value of delta S water from here and delta S reservoir from here, so after doing the substitution, so that is 0.06454 Cw minus delta S reservoir 0.0625 Cw. So it comes out to be equal to delta S1, that's the entropy change of the universe in process 1. So that is equal to 0.004 204 CW. So let's call this as equation 1. Okay, now let's come to the process 2. So process 1 is over. Now let's come to process 2. So in process 2, so the entropy change for the water in the process 2, what are the steps? The water is first brought in equilibrium with the reservoir at 310 Kelvin. So that means it's taking place in 2 steps. So first 300 to 310 Kelvin, and then in the next step from 310 Kelvin to 320 Kelvin. Okay. So here, if you just take a look at the initial and final equilibrium state of the water, that's same. Initial equilibrium state of the water, it's at 300 Kelvin, and the final equilibrium state, it's at 320 Kelvin. So that means the entropy change for the water, it's not going to be different as compared to the previous case. It's going to be same. So that means here in the process 2, delta S water, that will be same, which is 0.06454 multiplied by CW. It's not going to change. Whereas delta S reservoir, because process is taking place in 2 steps, so we will have 2 terms here. And in both of these 2 cases, the both reservoir, the one at temperature 310 Kelvin, first it will lose heat to the water which is at 300 Kelvin, and when the water has acquired a temperature of 310 Kelvin, so then again the water at 310 Kelvin will again gain heat from the reservoir which is at 320 Kelvin. The point is that both reservoirs which are at temperature 310 Kelvin and 320 Kelvin, they will lose heat to the water. So that's why a negative sign will appear while doing the entropy change calculation, and the corresponding entropy change is given by, that is, minus CW and delta T1. That's the temperature, delta T1. So I will, in a moment I will write what is delta T1, and divided by temperature of reservoir 1. Okay, so I'm taking this outside, plus delta T2 divided by temperature of reservoir 2. Okay, so this is further equal to minus CW outside, because it's the heat capacity of the water, and then multiply by delta T1. That's the, in principle, we are writing here delta Q of the heat lost by the reservoir, that is equal to heat gained by the water. Okay, so that's why we are writing here CW here. Okay, so 310 minus 300, that's a delta T when water is placed in contact with the reservoir 1 which is at temperature 310 Kelvin. Okay, plus now the second term, when the water has when the temperature of the water, it has reached 310 Kelvin and it's placed in contact with the reservoir at 320 Kelvin. So corresponding delta T will be 320 minus 310 upon 320. Okay, and after solving this, we will obtain, so this is equal to minus 0.06351 CW. Okay, so that the corresponding entropy change of the universe in this process, so that delta S2, that's the entropy change of the universe during the process 2, that is equal to delta S water plus delta S reservoir. So delta S water, it's same, so that is 0.06454 CW plus delta S reservoir, which is negative, so minus 0.06351 CW. Okay, and this upon calculation gives 0.00103 CW. So let's call this as result 3. Okay, so now the third case, that is process 3. In process 3, okay, the system is first the temperature is changed, temperature of the water is changed first from 300 to 350 Kelvin, and then it's brought back to 320 Kelvin. Okay, so during the first step, and see for the water again here, the initial and final equilibrium state, they are same. Its initial equilibrium state, it corresponds to 300 Kelvin, and final equilibrium states correspond to temperature of 320 Kelvin. So the entropy change for the water in this case, that is delta SW, it's again going to same. Okay, and that is equal to 0.06454 CW. It's not going to be different situation. Okay, whereas the entropy change for the reservoir, okay, it's going to have a slightly different expression. Why? Because first the water at 300 Kelvin, it's coming in contact with the reservoir which is at 350 Kelvin. So therefore for the first case, reservoir is going to lose heat to the water. And what is that heat that's lost to the water? So that will allow us to calculate the entropy change for the to reservoir. Okay, delta S reservoir, that is equal to minus CW, and delta T I'm writing, it's a corresponding, it's a temperature change for the first process, and minus CW delta T divided by temperature of the reservoir 1, which is 350 Kelvin. Okay, and then now the water has reached the level of 350 Kelvin. Okay, now the temperature has to brought down to the 320 Kelvin. So that means when we will place the water which is at 350 Kelvin in contact with the reservoir which is at 320 Kelvin, so that means water is going to lose heat to the reservoir. So that means there is a positive change in the entropy for the reservoir, because it's acquiring energy, heat from the water at 320 Kelvin, but its temperature is not changing. Okay, so that's why a positive sign here. And then CW delta T here, delta T, let me call this a delta T1 and delta T2 divided by the corresponding temperature of the reservoir which is 320 Kelvin. Okay, please try to understand this point. Okay, for the first step, reservoir is losing heat because it's at higher temperature as compared to water, but once water has reached the temperature of 350 Kelvin, and when we are placing the water at 350 Kelvin in contact with the reservoir at 320 Kelvin, so in that case the reservoir will acquire heat from the water at constant temperature of the reservoir which is 320 Kelvin. Okay, so therefore this is further equal to minus CW, and delta T1, it is 350 Kelvin minus 300 divided by 350. Okay, and then plus CW and delta T2. Now the water is at 350 Kelvin, 350 minus 320 divided by temperature of the reservoir which is 320 Kelvin. Okay, and after doing the calculation, so we will obtain that this is equal to minus 0.04911 CW. Okay, you can cross check these calculation, so that the delta S3, that is the entropy change for the universe during process 3, that is equal to again delta S water plus delta S reservoir. Okay, so that is equal to minus 0.06454 CW, sorry, it's with plus sign, and minus 0.04911 CW. Okay, so after solving it, we will obtain that this is equal to 0.01543 CW. So let's call this as equation 3. So if we compare equation 1, 2 and 3, so we will notice that delta S3, it is greater than delta S1 and it's greater than delta S2. Okay, so let's see which option it corresponds to. So 3 is greater than 1, 3 greater than 1, greater than 2. So that means option B is the correct option here. So let's continue with the next problem. The statement is 1 mole of nitrogen gas, the ratio for 1 mole of nitrogen gas, the ratio delta S1 by delta S2 of entropy change of the gas in process 1 and 2, which are mentioned below, is, so round off up to 1 decimal place. Okay, this, the first process is gas is held at 1 atmospheric pressure and cooled from 300 Kelvin to 77 Kelvin. So that's the first process. In the second case, the gas is liquefied at 77 Kelvin. Okay, so we have to calculate the entropy change for these two processes and then find the ratio, respective ratio. Okay, so let's see for the process 1, as the temperature is changing from 300 Kelvin to 77 Kelvin, and let's say the corresponding entropy change delta S1, that is equal to Ti to Tf and dq by T, that is equal to Cp dt upon T, because the process is taking place at constant pressure. Okay, from initial temperature which is 300 Kelvin to final temperature which is 77 Kelvin. Okay, so this is equal to Cp ln final temperature, that's 77 Kelvin, divided by 300 Kelvin which is initial temperature. Okay, and if you substitute the value of Cp, which is 7, which is given to be 7 calorie per mole per Kelvin. Okay, so delta S1 comes out to be equal to 7 ln 77 upon 300, and this is equal to minus 9.519839 calorie per Kelvin. Okay, so now for the process 2, which is taking place at constant temperature, corresponding entropy change delta S2, that is equal to dq by T. Okay, so dq, that's nothing but here that's Cp delta T. Okay, but delta, it's not Cp delta T, but it is the latent heat, because process is taking place at constant temperature. Okay, L by T, so latent heat, that's given as 1293.6, it's given here 1293.6 calorie per mole. Okay, divided by the corresponding temperature which is 77 Kelvin, and it comes out to be equal to 16.8 calorie per Kelvin. Okay, so let's call this as the equation 2. So now the ratio delta S1 upon delta S2, that is equal to 9.519839 divided by 16.8, and this is approximately 0.566, and this can be approximated as 0.6. so therefore this ratio, this is 0.6. that's the answer. So let's continue with the next problem. The statement is, a piston of mass m is fitted to an airtight horizontal cylindrical jar. The cylinder and piston have identical unit area of cross section. Okay, so that's the piston and the jar, they are having the same cross section area. The gas inside the jar has volume V and is held at pressure P is equal to P atmospheric pressure. Okay, the piston is pushed inside the jar very slowly over a small distance, and on releasing the piston performs, it's not undamped but it is undamped. Okay, so please note it is undamped. Undamped simple harmonic motion of low frequency. Okay, assuming that the gas is ideal and no heat is exchanged with the atmosphere, the frequency of the small oscillation is proportional to what? Okay, so let's see how we can solve this problem. So we are given a horizontal cylinder. Okay, so let me draw it first so that it will help us to understand the problem in a better way. We are having a horizontal cylinder and it's attached with the piston. Okay, so it's the piston here, and it's also given that the cross section area of the piston as well as that of the cylinder is same. Okay, so that means, so okay, so this also corresponds to the piston. Okay, so let's say the cross section area, that's A. Okay, now when in the equilibrium state, initial equilibrium state, we can say the volume of the gas which is inside this part, it is V, that's the volume V, and the corresponding pressure is P. Okay, now in the second stage, when it's given that the piston is pushed inside the jar very slowly. So when the piston is pushed, let's say through a certain distance, so that let me draw the position of the piston when it's moved by a certain distance. Let's say it's moved by a certain distance. Now let's say this is the new position, okay, and now it's moved by a certain distance, let's say dx or x, okay. So that means it's a basically compression, okay. So that the new pressure inside the chamber will be, it's going to change the pressure by a certain amount, let's say P plus delta P, and the corresponding volume, new volume will be V minus delta V, okay. And on releasing the piston, it performs undamped simple harmonic motion of low frequency, and we have to determine that frequency, that frequency is proportional to which factor, okay. So now let's figure out the solution. So that means we are having an initial condition, and then we are having a final condition, okay. In the initial condition, the pressure inside the chamber, that is P1, that is equal to P, and the corresponding volume B1 is equal to B. And when the cylinder is pushed by the piston is pushed by a certain amount x, so that the corresponding change in volume dV, when it's pushed by an amount x, the corresponding change in volume, that is cross section area multiplied by the x, the displacement, the horizontal displacement, that's a change in volume, okay. So that the pressure becomes P plus delta P, and sorry, it's P2 not P1, and corresponding volume B2, that is equal to V minus delta V, okay. And it's also given that assuming that gas is idle and no heat is exchanged with the atmosphere, because no heat exchange is taking place, no heat exchange, that means delta Q, that's equal to 0, so that means process is adiabatic. So we can treat the process to be adiabatic. So when we say adiabatic, so that means here PV power gamma, that's going to be valid, okay. Since we are having two different situations, initial and final situation, so we are going to apply this identity here for this process. So that means P1 B1 power gamma, that is equal to P2 B2 gamma, or P1 is P, P1 is B, PV power gamma, that is equal to P2. P2 is P plus delta P, P plus delta P, and then V2 is V minus delta V and its power gamma. So I'm taking P from the first expression common, that's 1 plus delta P by P, and then I'm taking B power gamma from the next expression, so that is 1 minus delta V upon B and its power gamma, and this is further equal to PB power gamma, and then inside the bracket 1 plus delta P by P, and then we are having 1 minus delta B by B power gamma, and we can rewrite this as 1 minus gamma times delta V by V plus higher order terms. We are neglecting because delta V is much smaller as compared to capital V, okay. So we can neglect higher order terms. So after doing the multiplication, so this comes out to equal to PV power gamma, okay, and then inside the bracket we will have, after doing the multiplication, so this is equal to 1 plus delta P by P, okay, and then the next term minus gamma times delta V by B minus gamma times delta P delta V upon PB plus higher order terms, okay. So we can neglect this term because both delta P and delta V, it's going to small, so their product is going to even smaller, so we are going to neglect this term, okay. So PB power gamma, it's on the both side, PB power gamma, so it will also cancel, so we are left with 1 here, okay. So that ultimately we are left with the expression which is 1 that is equal to 1 into 1 plus delta P by P minus gamma times delta V by V plus so on. Okay. Now after equating both sides, so we obtain from here, from this equation, we obtain, because 1 will cancel with 1, so ultimately from here we obtain that delta P, that is equal to gamma P times delta V by V. Okay, let me check whether I have given some equation number. No, so let's call this as equation 1. Okay, now it's given that after releasing the piston it performs simple harmonic motion, because after releasing the piston it executes simple harmonic motion. So that is the force that we are applying, or we can compare this with the restoring force basically. So F, that is equal to minus A times delta P. Okay, or which is equal to, now delta P we are going to substitute from equation 1, so that is equal to minus gamma AP delta B by B. Okay, so delta B, that is A, that is equal to A times X. Okay, so that is equal to minus gamma AP into AX upon B. Okay, so that this is equal to minus gamma A square P upon B multiply by X. Okay, now from here we can define the acceleration, that is force upon M, and that is equal to minus gamma A square P upon B, or MB, because we are also dividing by M, and then X. Okay, so that means, which says that acceleration is proportional to displacement, where the constant of proportionality, that's nothing but that's omega square, that's the angle of that's the frequency of oscillation. Okay, so that means therefore omega, that is equal to gamma A square P upon MB, and it's under root. So that means it's proportional to gamma P upon MB. Okay, so therefore we conclude that option B is the correct one. Okay, so let's continue with the next problem. The statement is, a paramagnetic salt of mass M is held at temperature T in a magnetic field H. Okay, if S is the entropy of the salt and M is its magnetization, then dg, that is equal to minus S dt minus dH. Okay, where G stands for the Gibbs free energy. If magnetic field is changed adiabatically by delta H approaching 0, so that is, it's adiabatic demagnetization basically. Okay, and the corresponding infinitesimal change in entropy and the temperature are delta S and delta T, then which of the following statements are correct? Okay, so we have to identify the correct statements among the given first options. Okay, so here the magnetic interaction energy, so let's continue with the solution. The magnetic interaction energy, that is given as minus M dot dH. Okay, remember H here, it's not the enthalpy but it's the external field. Okay, now we are also given a relationship between the Gibbs free energy and the applied field and the change in temperature. So the relationship is, that is dg, that's a Gibbs free energy for this system, that's given as minus S dt minus M dH. M stands for the magnetization, and okay, so here we notice that T and H, these are the natural variables for the Gibbs free energy for this system. So here T, that's temperature, and H, that's the magnetic field, these are the natural variables for Gibbs free energy for G. And we also notice that S and M, these are the redundant variable here. redundant variables for G. Okay, and I'm going to explain the meaning of these redundant and natural variables here. So from equation 2, what I can do is I can write S that is equal to minus dg by dt by keeping h constant. Okay, so when we keep h constant, dh will be 0, so that S that is equal to minus dg by dt. Similarly, I can also write M that is equal to minus dg by dh by keeping temperature constant. Okay, so the meaning of the redundant variable, by saying S and M to be redundant variable, it means they can be determined if we are having the idea about the changing Gibbs free energy with respect to temperature and with respect to the applied field. Okay, so in that sense we say that we call them as redundant variable, and natural T and H we are calling as natural variables. Okay, so now the point is that from here we will make use of the property of the Gibbs free energy, because Gibbs free energy G is a perfect differential. It's a perfect differential. So what does it mean? So that means it's differential with respect to its natural variables. Okay, it doesn't matter in which order we are performing the differentiation or the way we are performing the process, but the value of the this is the second order differential of G with respect to T and H, that's going to be same. That means in terms of mathematics, this is equal to curly T of dg by dh by keeping temperature constant and then by keeping fuel constant, and that is equal to curly h of dg by dt by keeping h constant and then outside by keeping t constant. So that means the second order differential of G with respect to its natural variable, if we change the order of the differentiation, but still the value is going to be equal, so that means it's path independent quantity. Okay, so now let me call these two results as equation 3 and this as equation 4. So now by using equations 3 and 4, so that means I'm going to replace dg by dh here with minus m, so that is, and on the other side dg by dt, that will give you minus s. So this minus sign that will settle, because we will have on both left hand side as well as on the right hand side. So that means curly t of dg by dh, that is equal to minus m. So I'm writing here m and then at constant h, and that will be equal to curly h dg by dt, that is equal to minus s. So I'm writing as negative sign, they will cancel, and here it's the constraint of constant temperatures. That means let me call this as equation 5. Okay, now I can write dt, the change in temperature with change in magnetic field, change in temperature with change in magnetic field dt by dh by keeping entropy constant, because that's what it's given in foundational change in entropy and the if the magnetic field is changed adiabatically. So adiabatically, that means we are going to keep the constraint of constant entropy, and by using the reciprocity theorem I can rewrite this as minus dt by ds by keeping the third variable constant, so that is h here, and then ds by dh by keeping now the other pending variable, which is t, as constant. So here we have made use of the reciprocity theorem. So what is the reciprocity theorem? So the reciprocity theorem it says that dx by dy at constant z, this is equal to minus dx by dz by keeping y constant, and then dz by dy by keeping x constant. Okay, so we have made use of this result here. So I can further rewrite this equation as dt by dh, dt by dH at constant entropy, that is equal to minus dt by ds at fixed field, and then ds by dH at constant t. Okay, this is by reciprocity theorem, and then this can be further rewritten as minus dt by ds at fixed h, and then ds by dh. So let's take a look at, so ds by dh we have already proved that by equation 5. This is equal to dm by dt at h. Okay, so I'm replacing it with dm by dt at fixed value of h. Okay, and this can be further rewritten as, this is equal to, so here we used the, while moving from here we made use of the equation 5. Okay, and this can be further rewritten as minus dm by dt at constant h divided by ds by dt at constant h. Okay, and this equation, this result, you can say, I can further rewrite, because this is basically equal to dt by dH at constant entropy. Okay, but for the finite change, what I can do is I can write delta t, that is equal to minus dm by dt at h divided by ds by dt at fixed h multiplied by delta h. That is the final result. But remember that this is basically the process that is described in the statement. It's basically the process of adiabatic demagnetization. Adiabatic demagnetization. Okay, so we have the change in temperature for the when delta h, which says that when delta h it's negative, this implies delta t is also negative. So this means when h final is smaller than h initial, this implies T final is smaller than T initial. That's it. The final temperature is lower than the initial temperature. And also during this process, because entropy it's held constant, so that means the entropy change delta S is also equal to 0. So therefore the options, so here option B, that's also correct, and option C, which connect delta E with delta H, that is also correct. So these two options, they are correct, but delta T it's not equal to 0. Delta T is basically negative in this process. So let's take a look at the next problem. The statement is, consider a non-interacting gas of spin 1 particle, each with magnetic moment mu, placed in a weak magnetic field V, such that mu V by kVt is much smaller than unity. So this is the condition that's given to us, and we have to somewhere use while solving this problem. The average magnetic moment of particle is how much? Okay, so we are given a spin 1 particle, S is equal to 1, and it's placed in an external magnetic field, and we are also given the condition that mu b upon kVt, this is much smaller than unity. Okay, now we have to determine the average magnetic moment. So while going through the theory, you might have encountered this expression, the average magnetic moment. Okay, that is given as kVt curly b of ln q. Note that it's b, it's a magnetic field. Okay, or this can be also rewritten as, because minus kt ln q, that's the Helmholtz free energy. Okay, so in terms of Helmholtz free energy, this is minus curly b of f, where f stands for the Helmholtz free energy. So let me call this as equation 1. Okay, so that means because the Helmholtz free energy F, that is equal to minus kVt ln q. Okay, That's how the Helmholtz free energy is connected with the partition function. Okay, so that means in order to determine the average magnetic moment, we must have an idea about the Helmholtz free energy, or in other words we can say the idea about the partition function for the system. Okay, where the partition function Q, that is equal to summation gi exponential minus beta ei. Okay, now for s is equal to 1, corresponding value for ms, these are plus minus 1 and 0. Okay, and the corresponding interaction energy of the spins when it's placed in a magnetic field, the corresponding interaction energies are minus mu v, plus mu v and 0. All this minus mu v corresponds to minus this ms value of minus 1, and plus mu v corresponds to the ms is equal to plus 1, and 0 corresponds to ms is equal to 0. So we are having three possible energy value, interaction energy value. Okay, so therefore now we can write the partition function Q, that is equal to exponential minus beta into interaction energy 0 plus exponential minus beta. So I'm going to write it as 1 by kt. Okay, so exponential minus beta into the interaction energy of mu into b. Okay, so that is equal to minus minus will become plus, so exponential mu b upon kbt, plus the third term exponential minus mu b upon kbt. Okay, and this will give a unity, and plus now these two terms, they will give us a factor of 2 cos hyperbolic mu b upon kbt. Okay, that's the partition function. Okay, so now the corresponding Helmholtz free energy F, that is equal to minus kbt ln q, and that is equal to minus kbt ln 1 plus 2 cos hyperbolic mu v by kbt. Okay, so that the average magnetic moment, let me switch to the next page. The average magnetic moment mu, that is equal to minus curly b, not beta. It's not beta, please note it. It is b, magnetic field, minus curly b of minus kt, minus curly b of minus kt ln of partition function, which is 1 plus 2 cos hyperbolic mu b upon kbt. Okay, so we have to simply perform the differentiation. So this is equal to so minus minus will become plus, so ultimately this will be equal to kbt, and then differential of logarithmic function with respect to magnetic field, that will give us 1 plus 2 cos hyperbolic mu b upon kbt, and then again 2 sin hyperbolic mu b upon kbt, and then again the differential of this quantity with respect to b, so that will give us another factor of mu by kbt. Okay, so this kbt, it will cancel with this kbt, so ultimately we are left with a very simple expression, which is 2 mu and then sin hyperbolic mu b upon kbt divided by 1 plus 2 cos hyperbolic mu v by kbt. Okay, that's the general expression for the average magnetic moment. But now here we have to make use of the approximation that's given in the statement of the question. And what is that? We are given that mu v by kVt, it is much smaller than unity. So that means in this approximation, what we can do is we can approximate sin hyperbolic mu v upon kVt as mu b upon kVt. Okay, because when this argument it's very small, so then the sign of that function, that's almost equal to the argument basically. Okay, and also in the same approximation we can approximate the hyperbolic function cos hyperbolic mu v upon kVt. This is equal to unity. Okay, so with this approximation in this expression, what we obtain is this is 2 mu and then divided by 1 plus 2 and then sine hyperbolic mu v by kt. So this is approximately equal to mu v upon kVt. Okay, or this is equal to 2 by 3 mu and then mu v by kVt. Okay, so this is the final answer. So let's see if we just take a look. Yes, so that means option A is the correct one here.